in this region of the activity thing, in this region, this material is going to be called ionic material. Ionic material. Okay? The electron and hole conduction is not important, and the ionic, with the most of the conduction is being carried out by the ions of the materials. Now, in a batteries, for example, the electrolyte should be the ionic material, right? In the batteries. Because in the batteries, what you're doing here is that you have a cathode and anode, and then you have an external circuit for the electrons and holes. But in this electrolyte, only ions should be moved. Only ions should move. So the conduction. So the electrons and holes should not pass through here. So this electrolyte should be the ionic material. And then if this material is in the environment of this region, then we are going to have a ionic material. But somehow, if you go outside this environment, then this electrolyte suddenly becomes the electronic conduction or hole conduction. So that this battery system is going to be completely ruined, goes out. Because internally the electrical circuit is going to be formed. So this happens, in liquid electrolyte, it does not happen that frequently, but in a solid electrolyte case, like a thin film batteries, all solid state batteries, things like that, then this material, the solid for this electrolyte, can be changed depending on the environment. And the overpotentials, if overpotentials happens in the vicinity of the anode or in the vicinity of the cathode, then that part of the electrolyte can be located outside this ionic region because of the decomposition, we should say, or formation of some element, which means the material is going to be located outside this ionic region. Then this battery is going to pass the current, internal current as well as the externally, okay? Then what we measure as the charge, discharge from the R circuit is not going to be the correct one, because some part is going to be transferred inside this material. So that is very important to keep the electrolyte in this ionic region somehow, okay, to make the battery useful. All right, I will give you some of the examples of this defect equilibrium diagrams as a homework next week on Monday, okay? Then you can have a better idea what we are talking about. If you solve some of the problems related to the defect equilibrium diagram, then probably you can get a better idea of this, okay? And let me just give you the relations between defect equilibria and overall composition briefly, and then wrap up this class, today's class. Defect equilibria and overall composition. Okay, we have stoichiometry, mx binary system like m b plus delta. Okay, and here the delta is a deviation from the ideal stoichiometry. Deviation from ideal stoichiometry. Okay, then m x total a of b plus delta. Okay. Now here the mass balance the cation concentration total is going to be the mm plus interstitial m, and then of course the x total is going to be xxxs plus xi things, okay? And the site balance and ratio of A to B site. Like it should be some finite values where m Vm xxx x. There is a site valence, right? But up to here, it goes without the saying, right? This is a very natural thing. And here, the deviation parameter delta now is equal to A xi interstitial x naught minus b and if you know the type of defects, then this becomes simpler. Like if you have a Frankel, say you have a Frankel disorder, then the major defects we know is going to be interstitial and the vacancies of the cation, so that the delta value now is going to be simplified to be mi naught minus phi m prime m t only. The other terms is going to be neglected, okay? And if we have a Seung-ki disorder, then the major defect is related to the vacancies and the vacancies of anion and cation, so that now the stoichiometry, deviation of the stoichiometry is going to be phi m prime a phi x naught m, things like that, okay? You know, in a battery system, the charge-discharge is related to the insertion or removal of the electroactive species to the cathode and the anode, right? So this insertion and removal of the electroactive species in the cathode, for example, during the charge-discharge reaction, it is related to the deviation of the stoichiometry of the material. Okay, if you insert the lithium into the lithium iron phosphate, which is a typical example of the lithium batteries, okay, and when you discharge, that means you are going to put some lithium into the LiFePO4, things like that, okay? So stoichiometrically, LiFePO4 is the cathode material in the lithium batteries, and when you discharge it, it means that you're going to put some lithium, add some lithium into this, so that now lithium is going to be 1 plus delta FePO4. It's going to change the material to this values. And then you're going to change the open circuit voltage of the batteries as you discharge, as you insert the lithium into this. Now when you charge this thing, what you're going to do is you're going to take out some of the lithium to certain values, PO4. Okay? And if you take too far or add lithium too far, then you're going to form the second phase, which is different from the LiFePO4. Okay? You are going to have a two-phase, you enter the two-phase region. It's more or less like a solubility limit in the binary system. If you have, let's say, if you have iron, this is a famous right? This is the famous iron and carbon system. Then at this temperature, there is a solubility limit, something like this, okay? At each temperature, we have a different solubility limit of the carbon into the iron matrix. Now, in LiFePO4, electrochemically, or precisely speaking, electrically, you insert some of the lithium into this material, but if you insert the lithium beyond the solubility limit at that temperature, then the second phase is going to be formed, okay? And the same thing happens vice versa. If you remove some of the lithiums to the certain limit, then you begin to form a second phase, okay? And whether you are in the two-phase region or in the single-phase region, the open circuit voltage of the battery system is different. It behaves different. We're going to talk about this later. But here what I try to emphasize is that this deviation from the stoichiometry by formation of the disorders, it will change the electronic material to the ionic materials, things like that, but as well as changing the electrical properties, it is going to change the phase as well. You know, the phase changes is not going to be depicted in the DED diagram. Defect equilibrium diagram just assumes that no second phase or no change in no formation or decomposition of the phases is not considered there. So in a practical sense, you have to take that into account, and this stoichiometry changes with the environment changes, like activity of the X2 changes, that has to be considered in thinking the defect equilibrium in a battery system. Okay, let's see. We are going to, next week, we're going to talk about a conductivity and the mobility thing a little bit more, and then we're going to discuss some of the examples of actual application of DED to the practical system. Okay? Okay, I'll see you on the next Monday, and then have